Boötes Void is the topic of today's video. By special request, somebody asked me to cover this topic, so I'm gonna look into it. They sent me the link so I didn't have to type it in, which is nice. Megaparsecs. Super void. So the Boötes Void is a spot in the galaxy. No, in space. What would you call this? Yeah, I guess just in space. Out there in the cosmos. The cosmos, that's a good word. It's found near the vicinity of the Boötes Galaxy, and it only has 60 galaxies instead of the 2,000 which should be there. So basically it's just like a big empty space in the cosmos where there should be a lot of galaxies, but there's only a couple. Apparently there are a lot of these voids out in the cosmos, and this one is the largest one. Here is a map of all of the other ones, if it'll load. Oh, come on now, I'm gonna have to zoom in on it. There's the Boötes Void right there, and here are some other ones. This is I'm not super intrigued by these voids. Why do you want me to look into this? So this right here is the Barnard 68, and this is often confused. No, don't do that. People often get confused, the Barnard 68 confused with the Boötes Void because it looks like a void, you know what I'm saying? Where are all them stars at? But this is actually a dark nebula where it's just not letting light pass through it, because obviously if there's an empty space in the cosmos, there's going to be stars behind the empty space that you can still see. This would make a cooler picture. I mean, it does make a cooler picture. So here's the actual Boötes Void. Come on, you butt. Show me the freaking picture. So in this picture, it's even harder to see. There's it's difficult to tell that there's even a void there because it doesn't really, I was thinking it would be like this level of density, star density all the way around, and then there would be like less, but nope, there it is. So the most intriguing part about this that jumps out at me right away is that there's no apparent inconsistencies with the lambda CDM model of the cosmos, cosmological evolution. So how are voids forming in the cosmos? This is saying kind of like soap bubbles kind of coalesce to form larger bubbles, and when they do, they leave empty spaces behind them. Let's look into how galaxies form, because I feel like that might be interesting, and that would give us kind of an answer on what's going on here. Dark nebulas could be interesting to look into as well. That sounds kind of cool. Dark nebula. How do galaxies form? I took astronomy in college, so I kind of have an inkling, if I remember correctly, but my memory is not great, so it's more my logic circuits that work better. Supermassive black hole. So I've never been much of a space fan, but black holes are freaking dope to learn about. I don't know what it is about black holes, but they're cool. And this is saying that the regular black holes generally weigh around 4 million suns. So if you had 4 million suns all condensed into a small space, it would be a black hole. What came first, the black hole or the galaxy? How can you ask that? I feel like it's pretty obviously the galaxy. Galactic cannibalism. So as I understand it, the way galaxies form is that there's a ton of space dust, like little tiny particles, and I mean, it's probably not that tiny. It's probably more likely like asteroid belt typed dust. Anyways, so over long periods of time, the gravity of those individual little pieces of space debris pull themselves together, and then as they get pulled together, they create more gravity because there's more mass there, and then that pulls itself together more, and then as the mass gets so intense, it crushes itself together, and then you get planets, and then those planets kind of pull together other planets around them. You got stars, and all of those things with their combined gravity, even though it's like very, very faintly pulling on the other celestial bodies, starts to pull everything together into a single entity, and that becomes a galaxy. So they're not all close together. Like in our Milky Way galaxy, everything is millions, or I don't know how many light years away, lots and lots of light years apart, but when you look at them from a long distance away, it looks like they're close together like a galaxy. So if you're having all those things pulling themselves together just by the act of pulling things together, you're also pulling things apart. So as you pull things apart, you get voids, you get spaces in between, and that's how you get things like the Boötes Void, where things were pulled in this direction towards the outsides, and all the stuff in the middle was left there. If I'm understanding this correctly, 62 megaparsecs, it seems like a long distance, 330 million light years across. Why does this Wikipedia page look so weird? There, that looks more normal. I'm struggling to be intrigued by this. I'm going to look up some interesting facts about this void. People are saying it's like mysterious, but there's not really anything mysterious about it. It's pretty self-explanatory, I feel like. If it was like a hole in space-time, like there was like a giant patch of dark matter there, I would be like, oh yeah, that's more interesting. But it's just like an absence of galaxies, right? Maybe I'm missing something big. Voids are great places to study neutrinos that freely stream across them. That's interesting. What are neutrinos? They sound cool. And why do we want to study them? There are massless particles? Wait, hold on, back up. I'm missing something. This is the kind of thing I'm interested in. Neutrinos typically pass through normal matter unimpeded and undetected. Are these on the atomic level? This might have just become a video about neutrinos. Alright, that's all the time I have for this morning. I'll come back later and let you in on what I found. See you then. The letting in on the knowledge time has arrived. Okay, so let's look at what I found. So I definitely decided to go the neutrinos route over the actually just looking into the void route, because there really was not that much to learn about the void. It's a void. So I looked into neutrinos and how they're related to cosmic voids. So first of all, let's see. Neutrinos are related to subatomic particles because they are subatomic particles. As we all know, right? Subatomic particles are things like the little tiny building blocks that make up atoms. You've got your electrons, your protons, your neutrons, and all that good stuff. This is the Bohr model. Apparently this one's outdated, but it's useful for depicting simplistic representations of atoms. Anyways, here you got your stuff. I was really struggling to figure out why exactly do we need to know things about subatomic particles? We know things about atoms. Why do we need to know subatomic particle stuff? And the conclusion that I kind of came to was that if you understand the building blocks of a thing, you can understand that thing better. I suppose maybe a crude analogy would be if you understand what makes up cement and how it works, you'd be better equipped to build a house type thing. So studying subatomic particles is important. It's a good thing. But we need to know how neutrinos are different from subatomic particles, because they're both part of the same category, but for some reason neutrinos are different. But why though? So I found out that neutrinos are super abundant. They're super tiny. I mean, they're the same size as a neutrino, or not a neutrino. They're the same size as a proton and neutron and whatnot. And they don't really interact with much other than some things that we'll talk about in a little bit. So this article was a little more helpful in understanding what exactly is going on with neutrinos. So neutrinos are formed by the atomic nuclei coming together and breaking apart, or breaking apart. So if in the sun, things are fusing together by fusion, or if things are breaking apart by a fission, by the process of fission, then that reaction will create neutrinos. Also, fun fact, things that are naturally radioactive will also produce neutrinos, like potassium. I don't understand why you would need something, you would give an example like the sun creating neutrinos or fission, and then lump that in with bananas. I don't understand. So another fun fact about neutrinos is that scientists think it's its own antiparticle, and I didn't know what an antiparticle was, so I had to look it up in the dictionary, and according to the Oxford Dictionary, an antiparticle is, a particle having the same mass as a given particle but opposite electric or magnetic properties. So every kind of subatomic particle has a corresponding antiparticle. Electrons, protons, these three different types, right? Maybe. I'm not sure. It's just important to know that most of them, pretty much all of them, have their own counter antiparticle, but neutrinos don't. They're on their own. They're so low. Another fun fact about neutrinos is that there are three different types. Each type of neutrino only interacts with the corresponding particle that is paired up with that neutrino, but they change between the three different things as they're traveling. So they're flying through space, and they are going through a constant state of flux where they are changing. It's called neutrino oscillation, where they are changing between these three states. But at any given time, they have to be in that state to interact with that other particle, which is kind of wild. Okay, so at this point I was I think I understand enough about how neutrinos are working to kind of start looking into how they factor into cosmic voids, which I think they're actually called super voids, not cosmic voids. I feel like cosmic voids sounds better, but that's just me. There wasn't anything useful in this article. This article was talking about how they've been watching neutrinos be released from supernovas. Although I was really not clear, why do we care? Why do we want to measure neutrinos that are being released from supernova? And the explanation I got from this article was that they are hoping to learn new physics. New physics. And they're kind of hoping that exotic particles are produced by supernovas. And if they can measure the amount of neutrinos that are produced, and they because apparently it's super predictable how to quantify the amount of energy that is released in a supernova. So if you know how much energy was supposed to be released and you measure it and you're hey, there's energy missing, it could point to exotic particles being created. Which I don't know what they're talking about exotic particles, if they're talking about new types of elements or if they're talking about like what I didn't. It doesn't say that, but new physics. At this point, my brain was like, "That's it. That's all she wrote. No more on this topic." So I started thinking like these voids are very, very big. I think in the beginning we talked about how big the Boötes Void was, and it was like 30 billion light years across or something like that. Maybe it was 30 million. I don't know, a very large distance across. And I was like, how can they tell when this void is like an insane distance away from the Earth? How can they measure these things? How do they get accurate measurements when we are not close to the thing you're measuring at all? So I looked it up. So I found this one first. This one wasn't very helpful, but it was interesting. So as light is traveling from distant galaxies, it will fall into the gravity well of the galaxies that it is passing through. And as it is falling into those gravity wells, it will pick up speed and start to go faster. And then as it is escaping those gravity wells, it will slow down because the galaxy is pulling on it from behind and slowing it down a little bit. But the interesting thing is that it does not slow down as much. It does not slow down as much as it sped up when it was coming in. So it's a net positive gain. So as the light is moving through the galaxies, it gets faster and faster every galaxy it goes past. However, when it goes into a void, it slows down. They lose energy in a super void. They lose energy going in and they gain it going out. So as the light is traveling into the void where there's no galaxies, they start to go slower and slower. And then as they are approaching the other side where there are galaxies and the gravity wells of those galaxies are pulling them, they start to speed up. But it's a net negative gain, so they're actually losing speed as they go through these voids, which I don't know how useful that is to know, like measuring galaxies, but I thought it was pretty interesting. They called it a net photon. I'm not sure why there's two nets here. It was not explained. Okay, so then we got into kind of a meaty one. This document was the most helpful, but not super helpful, but the most helpful. So as you are measuring the galaxy, you are the like science people who are currently like taking measurements and doing this stuff are using a ladder of a system. They're using like a tiered system of measurements so that things that are closer are measured via the first tier, and then farther away things are measured based on the second tier, and so on. But each tier builds on itself, so you have to be pretty confident that the original measurements that you have on the first one are accurate. Otherwise, the further up you go, the farther out you go, the less accurate your measurements are going to be in theory. So the first one is the stellar parallax. Why can't I highlight this? Stellar parallax. I'll highlight it on the side. So basically you do this. You make an isosceles triangle with the sun and the earth and the star. And then you measure that angle right here. That's called the parallax angle. And that angle will tell you how far away the star is. Don't ask me about the math because I do not know. But, so I'm not exactly sure why you would need both. Do you need to wait all the way around to take measurements on both sides of the Earth? Do you need to wait a year to get the correct distance, or can you just math it? I'm not sure. Also, what happens if the star is over on this side and like in line with the sun and the Earth? How does that work? I don't know. The second method is the standard candle method. Okay, standard candle. So basically this is like, we know how bright stars are, and because we know how bright they are, we can kind of guesstimate how far away they are. There's something called absolute magnitude and lumosity, which are different things, but I don't understand the difference, so I'm not going to tell you about them. There's also things called Cepheid stars. I don't know how to pronounce this, but they pulse and they get brighter or dimmer. And apparently this is like a big deal in taking measurements for stars. You have to know like how often and how brightly these things are going to pulse, these stars are going to pulse. But like, what the actual heck? Stars pulsing, like how does that make any sense? They're like more mass all of a sudden, so they get brighter, and then the mass gets burned away, so they're less bright, and it's at regular intervals? Like what? Like what? I don't know. I want to know why stars are pulsing. And the third rung on this ladder of measuring distances is the supernova, type 1 supernovae method. This one's much more complicated. This is like, it was difficult. But basically you've got this curve here, and it's curvy-worvy. And it's kind of like the candle. It's basically like a more advanced method of the standard candle where you can look at the supernova, and because supernova are super predictable in how they are going to like explode, and then how the energy is going to peak and then like drop back down. If you are looking at the supernova, you can tell how bright it is, and then you can gauge the distance from there type thing. I'm really not sure about that one. And then the fourth step is the redshift, which is like if you're looking at a star through a telescope. I'm not sure exactly where the red is shifting. Where is the redshift happening? Is it on the telescope? Anyways, I can't remember where I read about I think it's like on the telescope. If you're looking at something, there's like a tiny little bit of red around like the lens of the telescope as you're looking. I can't remember. I don't remember. Anyways, there's a redshift. If you're looking at the star and it is traveling away from you, it's going to have a red shift around the edges. If it's traveling towards you, it's going to have a blue shift. And this is how they figured out that most of the stars and galaxies in the universe are moving away from us. That doesn't make sense. But they're moving away, and the different color of the redshift determines how far away that thing is, which is kind of cool. Anyways, that's all my notes for this topic. Let me know if you had a good time. I will catch you on the flippity flip. Peace.